I would go to the mountain with detectors to see photons that left the center of the galaxy 30,000 years ago. Some miss Earth and continue into space, but some of them land on my detector, empowering me to deduce the nature of the galactic center.
Well, you gave your photons purpose. My photons gave their life for my black ass.
This is Star Talk, Cosmic Queries Edition. Neil deGrasse Tyson, your personal astrophysicist. Chuck Nice, baby. How you doing?
What's happening?
All right. It's a grab bag. You stick your hand in the bag. You don't know what you're going to get.
And
It
you
comes
just pull it out.
and it's random.
Right. Exactly.
All right.
So, and if it's a turd, it's your fault, people.
Turd.
If we pull out a turd, it's your fault. This is all you. All right. This is Joshua from Portland, Oregon. He says, "Hey, Dr. Tyson, Lord Nice. I'm Joshua from Portland, Oregon. I love the movie Sunshine, but the main plot..."
I haven't seen Sunshine.
I haven't seen it either. He says the main plot of reviving our sun by sending all of Earth's nuclear material to the sun seemed more than far-fetched and even a quite bit cheesy. Putting all the cheesy aspects of the movie aside, the movie did address what it would be like getting near our sun. My question is, if you've seen the movie, did the movie Sunshine get anything right when approaching close to the sun, scientifically speaking, of course? And if not, in your opinion, what would be the funnest or weirdest thing to know about being extremely close to our sun?
So, a couple things. So, first, I haven't seen the movie.
All right.
But based on what has just been told, I have comments.
Okay.
Our nukes are, well, we have fission nukes,
Right.
which are what we call A-bombs.
Right.
The sun has never been in the business of nuclear fission.
It's fusion.
Fusion. It
Right.
takes light elements into heavy elements.
Right.
We do that, but we still don't know how to control it.
Right.
So we have uncontrolled nuclear fusion, otherwise known as a
hydrogen bomb.
bomb. Yes. There you go. Bomb.
Bomb.
We're good at making uncontrolled nuclear fusion.
Right.
And the day we harness that and we get fusion reactors, that would be very inexpensive
It will be
fuel.
the beginning of a new era.
A new era. Yes, it would.
Because all of our energy problems will be solved.
Basically, that's correct.
Yes.
That's correct. So now you want to send our measly nukes into the sun and believe that's going to make a difference?
Yeah.
Okay, just for context.
Yeah.
Have you ever seen spots on the sun?
I mean, in the pictures.
Yes. Do you know what we call those?
Sunspots.
Sunspots. I ask easy questions here. All right. A sunspot is typically slightly larger than Earth.
Okay. Well,
So the sun has blemishes
bigger than our planet.
Our planet.
Yeah, that's crazy.
And you want to think that
you
our
think
nukes don't have anything to do with the sun?
Right. Yeah. Why not throw spitballs at it? Just as effective. Just as effective. Get a straw and just as effective.
Or if I could do a Chuck voice, it would be, you'd fire the nuke into the sun and say, this is delicious.
Exactly. Yeah. Wow. Plus, isn't it different? I mean, you can't start fusion from an explosion, right?
No, the explosion is the fusion.
That's what I'm saying.
Oh, but can you trigger it?
Yeah, I'm saying, because the idea would be
No, you can't trigger it because the outer layers of the sun are not hot enough to sustain it.
Right. Okay.
But at the center of your bomb, it was.
Right.
But
Just like at the center of the sun.
Exactly.
Yeah, because the fusion is happening at the center of the sun.
And not in the outer
and not
edges.
in the outer
Okay,
edges.
so here's how you prolong the life of the sun. And I got to see the movie to see why they were doing it, if the sun was running out of fuel or whatever.
Right.
There's an easy way to do this.
Let me guess. Now, this is me guessing, so shut up. All right. I'm going to say, since the sun takes hydrogen and fuses it so that it ends up with like this 4-proton that creates helium.
Yeah,
right?
4 nucleons.
4 nucleons.
So it's 2 protons, 2 neutrons.
So the 4 nucleons that creates helium. What you want to do is either send the sun more helium or send it more hydrogen.
Why send it more helium?
Well, because the next step after the helium is, that's where it keeps going from there.
Yeah, but sun won't.
The sun won't.
Only the high mass stars are going to take.
Get
The
out.
sun pretty much stops.
So the sun stops.
Yeah.
Oh, so I need to send the hydrogen then.
Oh, yes.
I should just send more hydrogen.
Yes.
Okay.
Okay. Now, where's it hot enough to fuse hydrogen into helium?
In the center of the
In the
sun.
center. In the center. Okay. So
I got to get to the center of the sun.
So if you run out of hydrogen
Right.
in the center of the sun, where is there more hydrogen?
If I run out of hydrogen in the center of the sun.
Yes.
Oh, maybe I can pull it in from just outside the center of the sun?
Thank you.
Right.
From everywhere else, in the sun.
Just pull it back in.
Okay.
Yeah.
So there's what's called convection.
Right.
Okay. If you can drive a convection deep inside the sun, bring fresh hydrogen down into the core, pull out the helium, then
You'll jumpstart the fusion.
you can jumpstart the fusion. And the sun, when it dies, it only used, I forgot the number, a few percent of its total hydrogen available.
Oh.
The sun could live for trillions of years if you
If
can
you
be
can
found
find
a way
to recycle
You don't have
it?
to find hydrogen from somewhere else.
No, just-
it's sitting there in the sun itself.
Wow.
Just get a way to get it like a conveyor belt.
Right.
Send it down into the core.
And now all you have to do is do that without burning up before you get there.
Okay, so now how do you get close to the sun?
Well, first you give it a call. You're like, hey, how you doing?
You need a shield.
Right.
Because what temperature is it in space? Because right now you have a thermometer. It's reading the temperature of what?
Whatever the room temperature is. You mean here on Earth?
Specifically. If I have a thermometer here and it says 72 degrees,
It's 72 degrees at that thermometer.
what is 72 degrees?
The temperature of the atmosphere. I don't know.
The air.
Yeah, the atmosphere. Okay.
Okay, you said it's the temperature of the room.
Right. No.
It is the temperature of the air around the thermometer. In that spot.
Right.
It's the air.
Okay.
All right.
Right there.
Okay.
Because it may not be 72 degrees over there.
Now, if I come over here and I'm near that lamp,
Oh, it's going to be a little warmer.
because that's an old-fashioned bulb,
Yeah, exactly.
okay?
Yeah.
It's going to be a little warmer because that's heating the
That's
air
given-
over
right
there.
there. Right.
Okay.
You go by the window, it's going to be a little cooler.
Okay, over there.
Right.
If you're in space, there is no air.
Right.
So what the hell temperature are you measuring?
You got to measure the temperature of the nothingness of space.
Correct. And space is not entirely nothing.
Right.
There is radiative energy moving through space.
Correct. Right.
Photons.
Right.
So
So it's got a little bit of a temperature.
it'll get a temperature if the thermometer is facing the sun.
Right. Because that's a radiative heat coming from the sun.
Correct.
Right.
And it's not the air,
Not
it's
that-
just
it's
photons
just
hitting.
photons hitting.
Now, the other side of the thermometer, well, if you had two thermometers that split, so one is facing that way, one is facing this way, that's facing deep space.
And it's just like, it's cold. Why is it so cold? Man, I'm burning up over here.
Yeah. Depending on your distance from the sun,
Right.
that'll be the intensity of the rays. It'll be hundreds of degrees on the other side. Okay. And as you get closer to the sun, the radiative flux is you want to know the official term, gets higher and higher and higher. That temperature will continue to go up.
Right.
As long as you're shielded and you're looking out on the other side, that temperature is going to stay the temperature of deep space, which is like the microwave background hitting it,
Right.
which is there at all times, or some nearby stars if they happen to be there. So temperature is a funny thing. Did we do an explainer on temperature?
We did.
I thought we did.
We did. We did explain on temperature.
Yeah, okay. And you put it on your lipstick? Mm-hmm. Yeah. Supple lips. You can't do Star Talk with
can't.
crackly
I don't want
lips.
the people talking about me. You know, right now, if I had ashy lips, there's some black people out there like, what is wrong with his lips? And I believe this brother on TV with ashy lips. His mother didn't. He didn't know his mother.
Who raised you?
Who raised you? Really?
Who's a comedian? That's his line. Who raised you?
you?
He's one of the comedians. So, if you want to get close to the sun,
You need a shield.
but the shield will be too cold for you, and the other side will be too hot. So what you really want to do is make a rotisserie.
You just, Oh, I'm cooking evenly. Tell you right now, if you want to, somebody baste me, please. Get the butter.
So you get pretty close if you're on a rotisserie.
You're on a rotisserie.
All right. But there's a point where you'll just burn.
Right.
All right. And there's a point where that shield wait a minute, this photon's hitting that shield.
Right.
Maybe it's very reflective, so it's not absorbing any, but it's not perfectly reflective. Some are going to get absorbed, and that shield temperature is going to begin to rise. And eventually it will radiate infrared back to the other side of the thermometer.
And burn you alive.
So, yeah, the sun, and then you reach a point where it is so hot, everything vaporizes.
Right.
Do you know what has the highest melting point?
Iron?
No.
I thought what is it?
No.
What has the highest
You
melting
never
point?
guess.
I'll never guess.
Carbon.
What?
Ain't that something?
Wait a minute. But in the
Have you ever tried to melt a diamond?
Oh, well, there you have it.
Yeah, put that on your stove and see what happens.
Yeah,
right.
exactly.
Carbon.
Yeah. Wow.
Has the highest melting point.
Look at that.
It's like 5,000 degrees. I mean, it's
Insanely high.
Insanely high. And that, so generally, if you're going to go near the sun, you want carbon.
We need a diamond ship. And it have to be piloted by a hip hop star.
Or Elizabeth Taylor, or what somebody who likes
somebody
diamond.
like that, yeah.
Or Carol Channing, yes.
Ice. There you go.
Yeah, so I have to go see the movie now. Thanks for that prompting. And maybe I can add more to that commentary. But otherwise, yeah, it'll vaporize you.
There you go.
No matter what. Mm-hmm.
All right. Very cool. Sunshine, the movie, I haven't heard of it. So Bill Rodwalt from Oregon, Ohio. Oregon, Ohio? Mm-hmm. Okay. He says, if we were to find a habitable planet within a few dozen light years of Earth, and we had the technology to send a generational ship to this planet, how likely do you think it would be that the first mission launch would be the first to arrive? It seems to me that improvements in propulsion technology might be such that technological advances may lead to later missions overtaking the earlier ones. At what stellar distances do you think this would become a practical consideration as to when to launch a mission?
I love that because, what he's saying is that you launch a mission today with your modern technology, and in 50 years, that's some old technology. Right. And then the next ship just passes you by.
The old ship.
Waves to you. Yeah. It's sorry about that.
And it's like you started out in a covered wagon, and then all of a sudden a Tesla's going by you. Like, what the hell?
And so that's a brilliant question. And I think if we're going to be past, it'd be because we have warp drives. If you have warp drives, you can take a warp drive to the location of the ship and bring everybody aboard and put them on the warp drive too.
Right.
I think in practice, that's how we would do it. We wouldn't just
you
leave them.
You wouldn't leave them like, see you. Good luck. No, you dock, you pick the people up.
Yeah, dock, you pick them up. And you put them
on with them.
You put them on the warp drive.
Right.
And it would have nothing to do with the propulsion. I don't see that as real.
Right.
Even if we found a way to, and we reached like 20% the speed of light, let's say, the nearest star to the sun is the Alpha Centauri system. Right. 4 light years away.
4 light years away.
So how long would that take?
20%, so that's 5 years for a year, 20 years.
20 years, very good math.
Yeah.
Good math. Loving it.
Every once in a while. Even a broken clock is right twice a day.
What'd you call it? You have a comedy special called Just Smart Enough?
That's my comedy special. Chuck Nice, Just Smart Enough.
You just got that one. So would you go on a trip for 20 years to a planet that might host you? I mean, so here's what I'd rather do. Mm-hmm. Whatever was the problem with Earth that you're trying to escape.
Yeah, fix it.
Just fix it.
How about that?
I'm just saying fix it.
All right.
And by the way, if that other planet is habitable, it means the atmosphere has oxygen in it.
Right.
What do you think made the oxygen?
Right. Yeah.
Life.
Of course. That's right.
But you get that you don't know what
we don't know where it
eat
came
you.
from.
You don't know.
Oh yeah, believe me, it's going to eat you.
Is it all life, but it's all Venus flytraps?
Right.
You know.
Yeah. Yeah. By the way, the fix it part is really the issue. It's like hiring a plumber. He's like, "Well, I found your problem. You're gonna need a new house." Like, what? What kind of plumber are you? Like, no. Yeah. So, well, what a great question, though.
Yeah, that's excellent. So it's a great question, but I don't see that as how that's going to play out.
Yeah.
Right. There's a moral question on a generational ship.
A life of isolation on a mission that they did not choose.
Correct.
But let's be honest, every kid said, I didn't ask to be here. I didn't ask to come here. I didn't ask to be born. Hey, all right, shut your ass up, man. Get over there to your station and do what you're supposed to do, okay? Because we got to get to this planet. Okay?
Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you? Or questions about anything at all? You can become a Patreon supporter of Star Talk. You have access to our exclusive question line on our website. Those are where we draw our questions for our cosmic friends.
Some of the most extreme objects in the universe.
Star Talk is a work in progress where we, every month, come up with some new way, some new idea, some new understanding of how to bring the universe down to Earth. We could not do that without your support. Thank you. And as always, keep looking up.
All right, here we go. This is Salvatore Mamana. Okay, from Brooklyn.
Salvatore what?
Mamana.
Spell it.
Mammana. Mamana.
Is that Mamana?
Mamana.
Yeah.
Mamana.
Salvatore Mamana.
Salvatore Mamana.
Yes.
He says, Dear Star Talk.
From Brooklyn.
From Brooklyn. Yo, Brooklyn born and raised.
Brooklyn in the house. Go.
I hope you are well. What do you picture in your head when you think of the Big Bang? I've heard it's not quite like the image of a tiny dot exploding in all directions. If you had to make a diorama for a 7-year-old, what would the Big Bang look like and what would yours be?
You know, I'm stuck on the explosion model.
Right.
But if you do that, it's exploding within 3-dimensional space. But this is a sort of a 4-dimensional with time as one of the dimensions. So I picture an inflated balloon. That's because that works for me.
Right.
You got to get rid of one of the dimensions. So our 3 spatial dimensions are flattened into the surface of a balloon.
Right.
And the time dimension is still there, emanating from the start of the balloon, where it's small,
to any surface point on the balloon.
And every larger surface point is later in time.
Later in time. Right.
Right.
Yeah.
That's how I do it.
Yeah.
So if you want to do it with your 7-year-old son, you get a nice big old one of these. Where do you get the really big? You have to go to a party store to get the biggest balloons.
The giant balloons.
Giant balloon, and on the balloon just draw galaxies on it.
Right.
And then inflate it, draw galaxies, and then deflate it. And as you inflate it back, you'll see the galaxies
spread apart.
Spread apart.
That's cool.
Yeah.
Yeah, that's the best way to do it.
I think so.
Yeah, I like it. All right. Well, thanks, Salvatore. That's a great. Do it with your kid, man, and tell him to give us credit for that A, because we know what you're doing. All right. This is Sotoris DeWitt from Belgium, and Sotori says, Hello, Dr. Tyson and Lord Nice. My name is Sotori DeWitt from Belgium. The name is Greek, but not me. As you mentioned before, space gets compressed near mass, and time at faster speed slows down. This I can imagine. But if space and time are connected, does that mean I would get smaller as I go faster? If so, I would be infinitely small at the speed of light. Would I then become light? Is maybe all light matter, but infinitely small and fast?
My boy's got some angst there.
I'm telling you right now. So first of all, Satori, it's going to be okay. That's number one.
There was some panic in that question, wasn't there?
Yeah, it's going to be all right, buddy. Okay.
The world will be fine.
The world's going to be all right.
All right. So time slows down for you as others would observe it, but you don't shrink.
Right.
Your dimensions will be measured to shrink front to back. So you'll get sort of thinner front to back as people measure your speed increasing. All right. They'll also measure your mass increase. They'll measure your time slow down. We have 3 equations that tracks all 3 of those. Okay. All that happens in a black hole. You're going to shrink only because it's compressing you down to a smaller point in space. So deal with it. I mean, that's there's not a way around that. And you're going to be stretched head to toe from tidal forces, but you're going to be squished shoulder to shoulder by the ever shrinking fabric of space and time until you descend into that abyss as a stream of atoms. Have a nice day.
There you go. Tell your kids that at bedtime.
So, yeah. And Einstein concluded matter can never go at the speed of light.
Right.
Because you have zero volume and infinite mass.
Right.
And time would stop.
Right.
So if you're going to travel at the speed of light, you have to have zero mass, like a photon.
Like a photon. Right.
Yeah.
There you go.
And they have zero mass, they travel at the speed of light, and they have zero time, which we talked about.
So, right. Well, a photon only knows time the moment it is manifested by something that it hits.
Right. So the photon is created in an atom.
Right.
It is absorbed wherever it was headed instantly.
Instantly. To it.
To it.
Right.
To it.
To it.
Yes.
Everybody else gets to see it.
Exactly.
Go its path. That's funny. And what I love is every time I'm on the beach, I always pull my swim trunks down just a little bit so that whatever photons land on my ass, I'm like, sorry, you were born in the sun and you landed on my ass in one instant.
You did. That is so mean of you to the photon. No, I had similar thoughts, but not so crude. Yeah. So my thesis data, my PhD thesis data, my thesis is right there.
Uh-huh.
Okay. We said the black one right there.
This one?
Yeah,
Oh, God. Jesus.
Yeah.
Look at that.
So a study of the abundance distributions along the minor axis of the galactic bulge. Okay. So this, it's single-sided, so don't think
still.
Point is, the galactic bulge is best viewed from Chile.
Oh.
Okay. Well, anywhere in the southern hemisphere. Mm-hmm. And I went to Chile many times to get data for this thesis. Here's the thing. The telescope is at the top of a mountain, which has a tiny coastal town called La Serena at the base of the mountain. Mm-hmm. La Serena has beaches. And the people would be laying out on the beach with bikinis on and things like that. And I would go to the mountain with detectors to see photons that left the center of the galaxy 30,000 years ago. Some miss Earth and continue into space. Others hit Earth, maybe the countryside. Some of them hit the buttocks of people on the beach. Mm-hmm. Like your buttocks that you exposed.
That's right.
But some of them land on my detector, empowering me to deduce the nature of the galactic center. So to me, those are noble photons.
Oh, you gave your photons purpose. My photons gave their life for my black ass. Okay. All right, here we go.
I can hear the photons say, what is this? Where did I just land? No,
All right, here we go.
all right.
This is Bodnar.
Actually, just to be precise, if it were like high energy photons, they were absorbed by your melanin.
Oh, wow.
Yeah.
Well, they were lucky then.
It would just grab it right out.
Right out, yes.
Snatch it right
That's
out of
what
there.
melanin is for.
Yeah, that's what it's for.
Yeah.
Mm-hmm.
All right, this is Bodnar Marton Janos, who says, from Budapest.
You can't possibly have pronounced any of that correctly.
No, Bodnar Marton Janos.
You could at least try to add a little.
I'm not trying to add anything to that.
Okay. All right.
He says, I'm trying to solve a dilemma I've been thinking about these past couple of days. Suppose I'm traveling in my super advanced spaceship towards a supermassive black hole at the speed of light with the goal of doing a gravitational slingshot maneuver at the black hole. I'm planning to do this speeding my spaceship close to the event horizon of the black hole. Questions. Is this even possible? If yes, how would I experience the event? 2. Using strong gravitational pull of the black hole and the slingshot maneuver, could my supersonic spaceship speed beyond light speed? I'm a 13-year-old student aspiring to be an astro or theoretical physicist.
Cool.
Good for you.
In Budapest.
In Budapest,
Yeah.
yes.
So, didn't we do an explainer
We did
on
slingshots.
On slingshots.
Yes.
Yes.
And it's really cool.
But it's not what you think it is.
No.
No. So
You know why? Because everybody thinks of slingshot as this.
Mm-hmm.
The two prongs that you pull, put a projectile, you pull it back, and then you release it, and then the projectile just goes, taking all the energy of the recoil from the pullback, propelling it forward. But the way you explain slingshots, gravitational slingshots, It's not really a slingshot.
It's not at all.
It's not really a slingshot.
So here's the problem. If you fall towards the black hole, but not in it, because you ain't getting out otherwise, the acceleration of the spacecraft falling into the black hole is exactly canceled by you trying to climb out the other side.
Right.
So when you're done with this exercise, you're not traveling any faster or slower than you were before. The slingshot works because you come in from behind an orbiting planet. And you go, the planet pulls you in, and the act of pulling you in has you catch up with it in its orbit.
In its orbit.
So there's an extra speed that's outside of the symmetrical fall in, climb out of the gravity.
Which is the planet itself dragging you along in its orbit.
Correct.
Right.
And you just ate some of the orbital energy of the planet by... You stole it.
You stole it.
You stole it.
By tagging up. You're a stowaway.
Gravitational stowaway.
You're a gravitational stowaway.
So that's not going to happen.
Right.
So A. B, if it's a supermassive black hole, you can easily fall into it and not be ripped apart.
Right.
Because the event horizon is
so big.
It's so big that the tidal forces are not strong.
Right.
So
you get in, and now you're just falling inside of the black hole.
You're falling within the event horizon of the black hole. And
the closer you get to the center, that's when
things start getting
that's when the tidal forces start messing you all up.
Correct.
But in the beginning, you're just like, oh, well, this ain't bad at all.
Not bad at all. And it's because your height, if he's in 13, maybe he's 5 feet tall, your 5 feet relative to the radius of the black hole is small.
Right.
Whereas as you get closer to the center, your 5 feet, there could be only another 5 feet to the center of the black hole. So the tidal forces will become greatly magnified under those situations.
Gotcha. Wow.
So,
but it's great to see a 13-year-old thinking like this.
Yeah. Oh, yeah.
How cool.
Oh, yeah.
How cool.
Yeah.
Well, good luck to you, man. And, invite us to your graduation. I mean, we're not coming, but invite us.
Stop.
I'm saying you're in Budapest. Ain't nobody who's paying that kind of money. We'll wish you well. But we'd like to know when you graduate. All right.
But wait, let me back up. So if I'm near the speed of light and I do an actual slingshot maneuver.
Right.
Okay.
Right.
Around a planet, could I be slingshot to go faster than light? The answer is no.
No. Yeah.
No, because you're not going the speed of light.
Right.
Because you're made of material substance which can't go the speed of light.
And it's not like the slingshot gives you all the energy and then you just keep it and keep going. You got to climb out of the fall the descent that you made. You have to now
that's exactly symmetric with it. So what happened was, let's say going 95% the speed of light, and you were to get a slingshot, what effect would it have? It would add energy to your trajectory. And there's a point where adding energy is not simply increasing your speed. There are other ways to boost the energy of the system. He will end up going faster, but he won't catapult past the speed of light. That's the way to think about it.
There you go.
Okay.
All right, here we go. This is Writer's Eye from Ohio.
Writer as in W-R-I-T.
As in writer, yeah.
Right.
Writer's Eye.
E-Y-E?
E-Y-E. So does the fact of us living in an expanding universe contradict the premise of living in the black hole? Since we know that black holes evaporate and there is a limit upon which all matter can be compacted, we wouldn't notice any intake of energy or matter from the waves it would cause. So not since the Big Bang has any more matter energy been introduced. Can we assume the universe in a black hole would not be expanding? Hoping to get an answer, lost in illiteracy in Ohio. That's very funny.
Nice.
Yeah.
So I don't have a good answer for that. If we were in a black hole and the black holes are eating things in its vicinity, you would see material coming in, just as he suggested. Yes. But not all black holes are actively eating.
True.
Quasars are galactic center phenomenon where the black hole is dining on stars and gases that have wandered too close, and it's emitting energy in the process. There's a distance within which quasars no longer are there. They shut off. We think they just completely ate everything in their environment. And so a black hole, it's not a requirement. It's not a prerequisite that a black hole is always eating things and you would then see things coming in through your event horizon. So don't use that as a reason for not embracing the possibility that we are in a black hole.
Gotcha.
So, and evaporation, supermassive black holes, forget black holes the size of our universe, supermassive black holes take 10 to the 100 years to evaporate.
Yeah.
So it's just don't hold your breath.
So we got time. A lot of time. Nothing to worry about.
Right.
So very cool. All right, but nice thought experiment. Here we go. This is Robert Dudok from Flint, Michigan. He said, I read a paper validating the subliminal warp drive as a more realistic possibility than the Alcubierre FTL drive.
FTL stands for faster than light.
Faster than light. Constant velocity physical warp drive solution. The one thing that was not even hinted at on the paper was how one might accelerate the warp bubble. I would appreciate any thoughts on acceleration and how fast the subluminal drive might eventually go, hypothetically, and thank you.
Yeah, I've got to do some homework on that. A couple of things. A warp drive, there's no prerequisite that it goes faster than light.
Right.
You just warp space and you go. But if you can go faster than light, then why not?
Right.
Like, what are you doing?
And if you were to go faster than light, this would be the only way you could do it, because you would have to compress the space, because you can't go faster through the space than light.
You're stepping through basically the compressed space on the Alcubierre drive. He was a Mexican physicist who came up with this. And so I don't know what the problem is, because the Alcubierre drive is a way to go faster than light, but there's nothing in principle preventing you from just dialing it down. Yeah, just go slower.
Right. Exactly.
Right? I mean, your car probably goes 130 miles an hour.
Guys, take it easy. You know, this part of the galaxy is a speed trap.
Red light cameras. So I don't see that as a sticking point at all.
Yeah.
Yeah, you just dial it down. Yeah.
Right. And by the way, even in Star Trek, they have warp 1 through 9.
Yeah, but warp factor 1 is the speed of light.
That is the speed of light, right?
Right, but I never hear them say warp. Oh, it's impulse power or something.
Impulse power is less than light speed.
Than light, correct.
Yeah. Yeah. So, all right, well, there you go. So you just fly on impulse, baby. All right, this is Tyrone Morgan from Hackensack, New Jersey. Joycey. He says, hello, Dr. Tyson, Lord Nice. Tyrone Morgan from Hackensack, New Jersey. Love your show, and here are my inquiries. What if the graviton was not quantum? What if the space-time that we live in is the gravitational field and black holes are the graviton in a higher dimension? Black holes having infinite mass at the singularity might be similar to photons having no mass in the electromagnetic field. Holy moly, bro.
Man,
you smoking some shit.
People.
Wow.
Oh my gosh.
What would a photon look like to someone whose space-time was the electromagnetic field? I think it's very difficult to see the full picture when you're inside of it. Thank you for everyone for the science that you do, curiosity, the passion, and your discovery.
I don't know if I can help this man.
This is a wild question.
He's got it bad.
Yeah,
right there.
man. The graviton.
Okay, so
the gravitational field and black holes in a higher dimension.
Just watch.
So wild.
So there's electromagnetic force,
right,
that is propagated by the photon.
Right. Okay.
They go hand in hand.
And
a photon comes in waves as well.
Of course.
We have gravitation. Einstein said it's the curvature of space and time. But if it's going to be a force and we're going to describe it in a quantum way, there ought to be a particle that propagates the gravitational field.
Right.
And we already have the wave that propagates it.
We've seen that.
That's called it's LIGO discovered.
Right, LIGO discovered it. Yeah.
Okay. So we got that. So what about the particle counterpart to the wave? We call that a graviton. Just like the photon is a particle counterpart to just the waves, light waves. Light waves, right. Okay? So we have a graviton is the particle counterpart to gravitational waves. But we don't know how to detect that.
Right. But it does make sense.
It does. Well, if you can turn all of gravitational physics into a quantum solution,
right,
then that makes sense.
Yeah.
But if not, it could just confuse things.
Yeah, I mean, I'm already confused, so, to be honest.
Yeah, so I think it's kind of fanciful to think of black holes as the gravitons of, it doesn't feel right to me. Because black hole, we already have that described. It's not some mysterious thing that you're finding some other mysterious thing to say that it is.
Yeah.
And we want to avoid that anyway. You don't want to take this thing that we barely know and to use it to explain this other
something
thing
else that we don't know at all. Take this thing that we really don't understand and barely know and use it to describe. This is what happens with
consciousness. People are saying, let's take the weirdness of quantum physics that nobody understands and use it to explain consciousness, which nobody understands.
Exactly. Right. Yeah. I mean, yeah. All right. Well, listen, I like the way you think, though, man. You definitely smoking some good weed. Please send me some. This is Matt D from Oklahoma, who says, "Good day, Dr. Tyson, and a big high five to Lord Nice. My name is Matt Dodd from Oklahoma, and I'm wondering about our bubble universe in the multiverse. If our universe is constantly expanding, does that mean our bubble in the multiverse is growing over time? Who's to say another multiverse bubble would not merge with our own? What would it mean for our universe? And thanks for the insight."
Yeah, I worry about that.
Yeah.
Because quantum physics in the multiverse model is pumping out universes left and right. And each universe has slightly different laws of physics.
Right.
You don't want to just, hey, let's go visit the Johnsons over in the other universe.
Right.
If the charge on their electron is different from yours.
Right, because now I just exploded. I turned to goo.
But you collapse into a pile of glue.
That's it.
So
they wanted us to come.
you bring something to test it with, like a gerbil or something.
So now somebody, I don't know.
That would be mean. Maybe not a gerbil.
No, gerbils are fine. Yeah, they ain't worth it. I'm not losing any sleep over a gerbil. Okay. Anyway, put that sucker in a habit trail, send them right through. All right. But
that other universe could be made of antimatter, for example.
Right. That would be terrible.
You toss it a coin and the thing blows up. Right.
That would be so cool. And then, of course, you meet yourself. But your other self, you look, has half of it is black and the other half is white. It's like
what episode from
Star Trek? The antimatter matter guy. That was very cool.
No, they'll have a goatee.
Yes, exactly.
And a black hat, that's the evil man.
Somebody, I don't know where I saw this or heard, because I don't think I read it, saying that, is there a possibility that dark energy or dark matter is another bubble universe colliding with ours, and that's why it doesn't interact, it's just passing through?
Yeah, I'm a fan of that kind of thinking.
Oh, okay.
Yeah, that's even though it involves a higher dimension, it's kind of simpler than other explanations.
It makes sense too.
Yeah.
It's like, this thing is just passing through us, but it doesn't interact because it's
like a sphere
passing through
two dimensions.
Right.
It's a dot, then a circle that gets bigger and bigger, then it gets smaller and smaller again, then disappears from your universe. So I'm partial to those explanations, even while knowing they're probably not correct.
Right. Fun to think about. All right. This is Sweet Heat 223 from Dallas, Texas.
Sweet what?
Sweet Heat 223, better known as Sterling from Dallas, Texas.
Sterling, all right.
He says, "Hi, Dr. Tyson and Chuck Nice."
So Sterling was not a cool enough badass name.
Yeah, he had to go with Sweet Heat. Or she. Sweet Heat. All right.
Sterling, that's a boy name.
Sterling's a boy name?
Yeah.
Okay, so Sterling from Dallas, Texas. He said, if we could travel via warp drive, is it possible that speed to bypass the spaghettification process when entering a black hole to reach its singularity? So, could you warp into a black hole and then bypass the singularity because you're going so much faster than the speed of light itself? So you've warped through the black hole. So technically, you don't need an escape velocity to get out of the black hole because you're warping through it. It's a wild proposition.
Are these two black holes?
No.
Just you.
This is you in the black hole.
Yeah, I'm not feeling it. Yeah, not feel. It's an intriguing idea.
It is.
And Like, can you bypass
the rules?
the
whole rules.
Yeah. The
No
boundary rules.
spaghettification.
Right.
None of the super
There are
gravity.
black holes that you can fall in and not go to the center.
Right.
They're like rotating black holes, and there are other configurations you can imagine. But yeah, no, I'm not feeling it.
Okay.
All right.
Yeah.
Chuck, got a few more minutes.
Okay, let's see what we can do.
Okay.
This is Patrick Laverdiere, who says, in video games, when you walk into a complex area, the frame rate drops because the system is rendering more data. If our universe were a simulation, could gravity be doing something similar, slowing down time because the cosmic engine is processing more information?
I like that.
Wow.
I like that.
He's saying the more complex areas of our universe
more slowly.
require more computing power, and as a result, everything slows down.
This is the argument either for or against that we're in a simulation, because the simulator doesn't have to simulate the whole universe.
No.
Only the universe that
you
you
are
perceive
seeing at the time.
Correct.
That's it.
For example, if we are in a simulation, are they simulating every molecule within the Earth if no one is looking at inside the Earth? But now you start digging, so it's in their interest to simulate ahead of you without having to waste computing power on the whole Earth.
Right.
And so that's just an intriguing scenario.
Yeah.
Yeah.
I mean, it makes sense. If you are in a simulation,
Right.
why would you waste all the computing power necessary to create the stuff that's never even being seen?
That's correct.
You know? Right. All right. So this is Merwaki Merwai. I don't know. Gerzeiger, who says, hello, everyone. I was wondering if black holes accelerate things beyond the speed of light once inside them. Does that mean those things are going backwards in time? So the gravitational pull is so strong once you are past that event horizon. Could you then go faster than the speed of light since light can't escape?
Yeah, what happens is you start gaining mass.
Right.
And rather than gaining speed.
Right.
That's how that happens.
How that happens. Okay.
Right. And so, no, you don't just keep getting faster and faster.
No. Okay.
And as you gain more mass, it's harder to accelerate you.
Right.
So, yeah.
Oh,
that's
wow.
not a thing.
But what a great question, man. I like that. All right. Femke Say naive from Belgium. He says, I was wondering, would it be possible to say if we reach a black hole with conventional space travel, even if it took thousands of years, to send a quantum AI computer or quantum robot, a bit like they did in Interstellar, ultimately sacrificing itself to send us the data and solve the quantum gravity theory? Could quantum computers handle this information and send it to a spaceship in the vicinity, or would the information forever be stuck in the black hole? Think you answered your own question.
Yeah.
Pretty sure you answered your own question, buddy.
Yeah. I'm going with it's stuck
It
in
ain't
the black
coming
hole.
out.
It ain't coming out.
It ain't coming out.
Yeah. I mean, there's the Hawking radiation, but it pulls it out as a striptease, right? One molecule, one atom here, one particle there.
Right.
And then you have to reassemble it later.
You would have to find that. You would have to put that information back together once it all evaporates.
Exactly.
Yeah.
Exactly.
Yeah. Oh, well.
I have time for one last question.
All right, this is Martin from Denmark. Martine from Denmark, who says, hello, Dr. Tyson, Lord Nice. Martin from Denmark here. I think there's something undiscovered around the perception of time and the speed of light. If we humans were to travel at the speed of light, we say no matter the distance, it will feel like an instant when arriving at the destination. But since we also discovered that we can accelerate particles faster than the speed of light, when did we discover that? The hell, Martin? Martin, did you get a Nobel Prize that nobody heard about? Because, damn, bro, what you talking about? And he says, how will we perceive that? Like yesterday, or thanks for a great show?
Okay, so no, we have not accelerated particles faster than the speed of light in a vacuum.
Right.
But the speed of light is slower
in mediums.
In media.
Right. Media. Right.
Plural of medium.
Plural of mediums.
Media. It's slower in water. It's glass, air, and especially diamond.
Right. Where it gets bounced around and then comes out.
When it's cut correctly.
Right, when it's cut correctly.
You're going to cut it in such a
So it
way.
refracts.
So it looks like the diamond has a certain radiance to it.
Right, yeah.
And it's refraction.
Yeah.
Yeah, that's exactly. And dispersion on the way out.
Right.
So,
Cost you a lot of money for a little bit of like praise. I stopped buying diamonds years ago.
and why are you forcing upon others your own marriage experience?
Just warning.
For those considering
If
tying
you're
the knot.
considering, just warning, I'm telling you. Cupid zirconia, man. Don't make the mistake. Don't make the mistake. The diamonds are expensive, buddy. Let me tell you something. They throw them on like it was no big deal. They don't put them on every time like, oh my God, look at this. This man went out and spent all this money on. They just throw them on like it's nothing to it. Okay? Get them zircons. Save yourself some money. Take it from a pro.
I forgot what the question was.
Okay. All right.
Oh, no. So you can't make them faster than the speed of light.
No.
So, but 2 points. If you could, the particles would go backwards in time.
Right.
According to the
According to the mathematics.
Right. So in Einstein's equations, you can go up to the speed of light, but you cannot attain it. But nothing stops you from existing on the other side of the speed of light and then going faster than that.
Right.
And if you do that, you would live backwards in time.
And what's that called?
Tachyon.
Tachyon. That's
Yes.
right.
Tachyos from the Greek, meaning fast, like a tachometer.
Right.
You've heard of
Yeah,
tachometers?
so of course, on your car.
Exactly.
Yeah.
It's the
Well, my car doesn't have it anymore because I have an electric car, so there's nothing to tack. Yeah, I'm just saying.
Okay. So then it would be moving backwards through time. And you could then send yourself a signal.
Using your tachyons.
Using tachyons before you knew to send yourself a signal.
Wow.
Yeah.
Trippy.
So, it's a fun particle. Someone decided to move all the way into the other side of the equations and follow them through. And that's one of the conclusions. We've never found tachyons
Right.
in the actual universe.
Oh.
Yeah.
Oh, well. It's kind of cool. So tachyons then, if they did exist, they would be moving. We could only intersect them at the point which they meet our reality
Going opposite directions
in opposite
time.
directions.
Correct.
That's the only time we can see them.
It's a perceptive point you're making.
Yeah.
You can't see them in the future.
You can't see them in the future. You can't see them in the past.
You're going to see them as it's going backwards through time, and we're going forward through time.
And boom, that's where you see the tachyon.
In that instant, that's correct.
That's wild.
Yeah.
I like it. Well, thanks for that, Martin from Denmark.
Yeah.
Very cool.
All right, I think we're done here.
All right, that was fun.
Man, we just knocking these out.
We love the grab
They keep
bags.
coming in.
Well, listen,
We're here.
As long as you keep sending them, we'll keep doing it.
There it is. Another installment of Star Talk Cosmic Queries. Grab Bag Edition. Neil deGrasse Tyson, you're a personal astrophysicist. Chuck, Lord Nice in the house.
Yes.
Thanks for being here.
Always a pleasure.
As always, keep looking up.